Hello everyone. My name is Karolina Krasa, and today I'm going to present you our results about graph homomorphisms in bounded-treewidth graphs, list homomorphisms in bounded-treewidth graphs. So let me share my screen with you and hopefully stop sharing my face. Okay, so as you can see, this is a joint work with Marta Piecyk and Paweł Rzążewski. We are all from Warsaw. However, this affiliation stuff is a bit tricky here, as you can see. Okay, sorry. So I will just proceed with basic definitions. So what is a graph homomorphism? We have two graphs, G and H, and the graph homomorphism is a function from the set of vertices of G to the set of vertices of H, such that the edges are somehow preserved, right? So if something is an edge of G, then it is mapped to an edge of H. Here we have a small example. So this is a graph G and this is a graph H, and we represent the vertices of H with colors. And this way we can just look at the homomorphism from G to H as some coloring of the graph G, which additionally have a property that if some colors are represent the end of an edge in G, then it must be an edge in H. Yeah, so I can have a blue-red edge here because there is a blue-red edge here, but I cannot color this green vertex of G yellow because there is no yellow-blue edge in H. And if there is a homomorphism from G to H, say this is a homomorphism H, little h, then we denote it like this. So this means that H is a homomorphism from G to big H. Yep, and and if the graph H is a clique, observe that this basically means that all distinct pairs of colors are possible at the end vertices of the edges of G. So this basically means that if H is a clique, then this is equivalent to the K coloring problem. So if there is a homomorphism from a graph G to K clique, then it is equivalent to the fact that G is K colorable. And because of this, we use the term H coloring for a homomorphism from G to H. And if there is a homomorphism from G to H, we say that G is H colorable. Okay, now I will quickly recall what we do know about the complexity of these problems. As for K coloring, we all know that it is polynomial if K is at most 2, and otherwise it is NP complete. And while the brute force algorithm gives us K to the n upper bound, we also know that we can get rid of this K, and there is an algorithm working in time 2 to the n. And on the other hand, there is no sub-exponential algorithm for K coloring. And as for the treewidth, the standard dynamic programming of tree decomposition gives us this K to the treewidth upper bound. But on the other hand, there is a theorem saying that this bound is optimal, right? We cannot just have something smaller here in the base. So a natural generalization of this K coloring problem with respect to homomorphisms is hom H problem, in which we have like a fixed H. Yeah, so for each H, this is a different problem. And for a given instance graph G, we ask whether there is a homomorphism from G to H. The P versus NP dichotomy for this problem was proven like 30 years ago. So yeah, if H is bipartite or it has a loop, has a vertex with a loop, then it's polynomial, and otherwise it's NP complete. This part is rather trivial, and this one is really complicated. And yeah, and again, we can have a brute force algorithm for this problem, which works in time the number of vertices of H to the n. But unlike in the case of K-coloring, when we assume the ETH, then we cannot find like a constant which does not depend of this H. Yeah. In the previous case for K-coloring, there was we could just replace this K with 2, and here there is like no universal constant which would work. And when it comes to the true width, again we have a standard dynamic programming on a tree decomposition, but there is a question if this bound is optimal. But for now, let's just say that it's complicated. And in our work here, we consider a further generalization of this hom H problem, in which each of the vertices of the instance graph is additionally equipped with a list of vertices of H, for which it can be mapped. Yeah, so it's just an analog of list coloring. That we only allow V to be mapped to some subset of vertices of H. So this problem is NP complete for graphs which are non-bi-arc graphs, and I'm not going to define the class of the bi-arc graphs now, as we don't need it, but you can certainly find it somewhere, for example here. And yeah. And again, since the size of the list is certainly bounded by the number of vertices of H, we have the brute force algorithm working in time the number of vertices of H to n. And since this list homomorphism problem is like a generalization of the non-list homomorphism problem, the previous one, and then the lower bound just transits from that problem. And finally, let's consider the complexity parameterized by tree width. So again, there is like a standard dynamic programming working in time the number of vertices of H to the tree width. And we are interested whether this bound is optimal or not. So in particular, we want to answer the following question. So for every graph H, we just want to find a constant which must depend on H, such that this L hom H problem can be solved in time L to the tree width, but cannot be solved any faster, assuming the SETH of course. So yeah, and since I'm posting this question in this form, you can probably imagine that there are cases for which this is not the optimal bound. Yeah, but for example, if we have as a simple corollary from the SETH-based lower bound for K coloring, gives us that if H is just a K click, then we have the list K coloring problem, and as we saw on previous slide, there is no K minus epsilon to the tree width algorithm for it. So our L equals K in this case. On the other hand, it is just straightforward, I think, that we can replace this H just with the maximum size of the lists, right? So for H prim like this, observe that we can always have lists of size 3, right? As every homomorphism which maps something to this vertex of degree 1 can as well map it to those vertices of degree 2. So we can always for every instance which has lists of degree 4, we can find in polynomial time an equivalent instance which has lists of size 3, just by removing this vertex from the list. And on the other hand, since this graph has a triangle, then from the previous case with k-click follows that it must be, this L must be at least 3. So this is equal to 3, and this is not the number of vertices of H prime, right? Right. So this problem was primarily considered by Pavel, who is one of my co-authors here, together with Laszlo Egri and Daniel Marks. Forgive me if I did something weird with the names, but hopefully not. And they managed to solve the case in which we assume that H is reflexive, yeah. So this means that each vertex of H has a loop. It's probably interesting to mention here that while the non-list version of homomorphism problem, when we have an H which is not reflexive, but it is enough that it contains only one loop, and then it is not only polynomial, as we saw before, but simply trivial, as we can just map every vertex of G to this one fixed vertex with a loop, and this is a homomorphism. But with list, the situation changes, as we may not have this vertex on the list, and then what? So yeah, there are many reflexive non-bi-arc graphs, and so this question is still very, very interesting even for reflexive graph H. So this case was solved in 2017, and it is probably also worth to mention that those reflexive graph H were also the first step in the P versus NP dichotomy for list homomorphisms. So this step was somehow natural. And then Pavel continued working on this problem with his two students, me and Marta, and we managed to solve it for the remaining graphs H, basically for all graphs H, as our proofs also cover this reflexive case. And today I'm going to show you some tricks from our proofs, but just restricted to the case when H is bipartite, as this is very easier and oops, I spoiled. This is much easier to say about it, and it was somehow the base case for our approach. And just as a quick recall, on some previous slide, I posed an analog question for the non-list variant, and with Pavel, we also did some serious work with that one. So if you are interested, I'm just shamelessly advertising our another paper, which was on Soda this year. Okay, so the first trick for list variant, which is non-trivial, but I think it's very intuitive, is the notion of incomparable vertices of H. And we already got a quick glimpse on those when we were talking about this H prime graph. Because this is just the incomparability in the neighborhood inclusion relation, right? So imagine that this happens somewhere in H. We have a red vertex and a blue vertex, and the neighborhood of the red vertex is contained in the neighborhood of the blue vertex. Therefore, if they both belong to some list, we can always just remove the one whose neighborhood is contained in another's one neighborhood. And I think it's easy to see that this is a safe reduction rule, because if there was a homomorphism using A, then now we can just use B instead. And if there was no homomorphism at all, then we just removed some vertices from the list. So there is still no none. Yep. So this is like a safe reduction rule. Okay. And now, what is an incomparable set in H? So this is just a set of vertices which are pairwise incomparable with respect to this neighborhood containment relation. So this basically means that set S is incomparable if there are no two vertices in it, such that no two vertices A and B, such that the neighborhood of A is contained in the neighborhood of B. And we denote by I of H the size of the largest incomparable set in H. So since this reduction rule I told you is safe, we can safely assume that the size of the list is also bounded by this I of H. Since each list we can safely assume that each list must be an incomparable set. So basically this yields a better upper bound for our base, as you can probably imagine that I of H can be much smaller than H. And another important thing which plays a role in our proofs is that if we assume that our H looks somehow like this, here we have bipartition classes H and Y, because recall that we assume that H is bipartite, and the vertices of H are partitioned into three sets, D, N, and R, such that N is a big separating D and R. And moreover, all vertices of D are complete to the corresponding part of N, right? Because it's bipartite, so the vertices from the class Y are complete to the vertices from X cap N, and symmetrically those vertices are complete to those ones. Yep, and now if we consider an instance G of our problem, we can just draw it like this. So let Q be the set of those vertices which have non-empty intersection with the set N. Yep, and let's just C1, C2, C20 be the connected components of G minus Q. Clearly, the list of those vertices don't contain M, and the lists of the vertices of Q don't contain D, the vertices from D, right? Because any vertex of D with vertices of N forms a comparable set, and we can just safely remove these vertices from D. So. And we also observe that each of these component, as they are connected, must be mapped like entirely for D or for R. Yeah, because it's connected, it cannot be mapped just some part of it to D and some other part to R. So the coloring of H coloring can look somehow like this, for example. And now we consider a following procedure for each CI. This component, we just check whether it admits a homomorphism to D, to H of D, to the graph induced by D. And then we construct an instance of L hom H2, where H2 is a graph obtained by H just by replacing those sets dx and dy, if they were non-empty, by vertices, and if they were empty, they are still empty, right? And this edge, we draw this edge if and only if there was some edge between dx and dy going. So this is like an induced subgraph of H. Yep, and we construct a new instance G of L hom H2 as follows. we only modify the lists of the vertices of those Cs, because if there is a homomorphism from Ci to D, we replace the lists, the vertices from D on the lists by dx and dy respectively, depending on the bipartite class. And if there is no such homomorphism, then we just remove the vertices of D from the lists, yeah, as we won't use them anyway. Great, and okay, we already observed that H2 is an induced subgraph of H, and H of D is also an induced subgraph of H. So we reduced our problem to polynomially many instances of those two problems, and we can just keep decomposing those obtained graphs until they become Bayer graphs or undecomposable graphs, which here means that either it doesn't have such decomposition, or have a trivial one, in which those the x and the dy sets are just singletons. Yeah, and so then if we want to decompose, then H is equal to H2, and it doesn't make sense. Yeah, so what we do then is that we just keep decomposing and obtain like a tree of decompositions, such that this H is in the root, and in the leaves we have biarc or undecomposable graphs. And then we prove this lemma, which basically says that we can just glue the solutions together, like from leaves to the root. Yeah, so this leads to the definition of I star, which, as you can see, is just the maximum over the size of incomparable sets over some specific subgraphs or induced subgraphs of H. And also we can prove that if H is indecomposable, then I star is equal to I. So since we had an algorithm working in time I to the tree-width, then for undecomposable graphs we have an algorithm working in time I star to tree-width. Yep, and so we just solve it for the undecomposable graphs and for Bayer graphs because it's polynomial, and then glue the solutions to obtain a solution for a graph which was decomposed. Okay, so I agree that this parameter might look strange, but on the other hand, we managed to do a reduction which says that this bound is essentially optimal. And this is very technical at some point, but after some careful analysis of the family of forbidden structures for the Bayer graphs, yes. So if we have a graph H for which L hom H is NP complete, then it must contain some forbidden structure for Bayer graphs. And we constructed for the undecomposable H, we constructed something called H gadget. And this is basically a graph with two distinguished vertices X and Y, such that each mapping from X and Y to the vertices of H can be extended to the mapping of whole F if and only if this mapping initially on X and Y they were mapped to distinct vertices, right? So using this gadget, we can just do a standard reduction from the coloring problem. And so if H is undecomposable, we just take the I of H coloring, yeah, because I of H is the size of the biggest incomparable set, and we just take an instance of this I of H coloring and replace each edge with this edge gadget. And this is the biggest incomparable set from H. Yep, and this is for undecomposable graphs, but this can be also done for the graphs which admits a decomposition, because in this definition of I star we just go over all indecomposable, undecomposable subgraphs, and because each instance of some subgraph, each instance of the problem L home H prime, which when H prime is some subgraph of H, is also an instance of L home H. So the lower bound with I star work for all H. Okay, so I guess that this concludes the details of our proofs I wanted to share with you today. As for general comments, let me just mention that we believe that our methods can be somehow used in different ways, as long as we can probably provide some lemma similar to this one in the first triangle, right? So we can, for example, try different parameters. For example, our lower bound works with path width, of course. We can also try different graph classes, which is probably somehow connected to this previous thing. And also we can just consider switching the problem, because there are many known variants of graph homomorphisms, and this stuff is, we believe it's general enough just to catch some other structures. Okay, so I guess that's all what I had for you today, different problems. So I'm showing my face again and stop sharing my slides. Thank you for watching. Don't forget to subscribe. No, thank you for watching, especially if you survived up to this point. And I would be grateful for any questions or any feedback regarding my talk. Bye.